Testing, testing. Yep, we are up. Alrighty, then. Okay. Alright, cool. I was just testing that. Did that work? I don't know. Okay. Okay. Okay, so yesterday we talked about, I mean, I said I'm gonna do something. I'm gonna go offline and try out these questions myself and then discuss with you guys. So I did that yesterday. So the question was to design a LRU cache uh, where you have the get function which gets the value of a key and a put function which puts the value of the key. Now, how it should work is when you get a key, it should become the most recently used item, and if your cache is full, then you remove. Sorry, that doesn't matter. Yeah, and yeah, what the put function would do is if your cache has space, then put it as the most recently used item, and this will be what will be uh, like basically at the top of your recently used list. Let's see what data structures we actually use, and the get will yeah, the get will, sorry, be getting that key. Uh, and what put will also do is in case there is no space in the cache, then it would delete the least recently used item. Basically, say if you have a list where you are keeping, the most recently used at the top and the least recently used at the end. So you remove the last item and you push this at the top. So, okay, so let me see what was my thought process when I solved this uh, question. So let me bring up the pad. Yeah. Okay. So, like I said, sorry. So, yeah. So basically, um, and the follow-up is if we can do it in O1 time. If both the operations we can do it O1 time. So now we know we have to use a map somewhere because maps are the best O1 uh, uh, tools. So now, okay, so let's just start writing those things down. So we need a map, right? And it'll be a key to value map. Now you can keep uh, now to decide if this map is going to also maintain the order of our cache. So And now a map can be sorted. You can basically, while declaring the map, you can give a sort function to define how that map is going to be sorted. But now this map has key and value, and it can be sorted using only those two. But our logic depends on, say, something like date of insertion. So we can't really use our map to determine the order of our of our LRU, the order in which the like basically when was which was the most recent item and which was the least recent item. So let's just say we keep our map to store the data. Now to um, store the order in which the item was most recently used and least recently used, uh, we can keep a different data structure. So essentially, what we need is to maintain an order, and also while maintaining that order, let's look at the function that we're going to have to execute, which will update these items. So say we use get. Now get is going to fetch from the map and return the value. If it doesn't find the map, then it returns -1. So uh, that's not complicated. Okay. Um. Yeah. So the get is not going to do much any change to the map. The change that we're gonna do on our other data structure is, say, so let's say our data structure maintains the order in which our items were recently used, most recently used. So at the first position, it contains the most recently used item, the next most recently used, and so on. So say we access the item 2. So how 2 is going to become the most recently used item is, first we can remove the 2 from this list. Uh, if we find 2 in this list, which means we can update the list itself without removing it from our cache, without removing any other element from our cache, because obviously get is not supposed to do that. That's port's job. So we can just remove the 2 and put it in front of the 1. So now 2 is the most recently used item, and 1 is the second most recently used, and so on and so forth. So what get is going to do is going to have to find, so it's two operations: find, not really two, find the key in our data structure. 2 is going to have to remove that key, and then it's going to have to add to front the same key. Okay, so that was get. We've still not decided what this data structure is going to be. Uh, let's see if put can help us decide. So what put is going to do to our map. So let's say the maximum capacity of our map is given. Now, if the capacity has been fulfilled, then we can't add to the map without removing anything. So what do we need to remove? We need to remove the least recently used item. So first we'll look in our data structure. Let's draw it again here. as to what the what the least recently used item is. Now that item is always going to be the last element in our cache. So what we need to do in this data structure is remove the last element and add the key of the new element that we want to put. And then using this element that we have removed, this also needs to be removed from our map. So this is the key, so we can find it in the map again and then remove it from the map, and then we can just add the new item in the map. So what put is going to do is uh, rem remove from our data structure, find in map, sorry, find it in the map, then remove it from the map, and then finally add new item to map, as well as add new key to the front of our data structure. So since we already decided that this is going to be a map, what operations are we doing on the map? Let's say we add an item, we remove an item, we find an item, and yeah, that's it. So finding in map is constant time O1. I think adding to the map is also constant time. Now I'm not sure how what removing is. Um, but if finding is one, then I don't think removing should be problem. So I think all operations on the map are O1. So we are good on that. Now we have to make a data structure that gives us O1 ideally for these operations. So we need to add to that data structure. We need to remove from that data structure. We know we always remove the last element, so that's fine. And we need to add to the front, and we need to find and remove as well. So if you only look at add and remove, which is done here, so we add to the front and remove from the end. So we already know front addition and end removal is great for queues. So we could have used a queue here. Sorry, I think I'm talking in reverse. Remove from end. So yeah, so something like an opposite of a queue. So we can use a queue to do that. Or but finding an element and then removing that element is not really possible inside a queue in between. So we can use, say, a linked list where finding is on and removal is would also be on. Adding is o1, adding to the front, and removing from the end is also o1. Oh, it's on. Sorry. Now, say we take a doubly linked list, then removing becomes o1, and yeah, at one position, finding and removing, um, it is on. Let me just show you the data structure that I'm talking about. Hey, thanks for following. Um, okay, yeah. So, like I said, a doubly linked list, which is a list in C++. Mm, if you see the documentation around the time, uh, Lists allow constant insert time and erase operations anywhere within the sequence. So since insertion and erase operations are constant anywhere, so I guess we can consider find and remove also to be O1. So since all our operations are O1, I think we can safely say that both our operations put and get are going to be O1. So the data structures we used for storing the data of the LRU, we used a map, and for storing the information about the least recently used data, we used a list. As you see, a list is implemented as a doubly linked list. Yeah. And we can just keep, say, an internal private variable to store the capacity. And we can either, there's other ways as well, or we can use another variable. Uh, Sorry. We can use another variable. Um, yeah, we can use this capacity to store the capacity, and we can use the size to store the current size, actually. And as soon as the current size becomes capacity, we know that we can't just add to the uh, map or our list. We need to remove some items and then add and update both of these accordingly. Okay, so yep. So here is the implementation that I did yesterday. I did it on leetcode, but I couldn't sign in from that machine for some reason, so I had to put it on IB for that for the time being. Mm, Key, value, key, that's all good. We can make all these private variables and then just set the capacity to in the constructor. And yeah, so okay, let me show you what I did. So you find it's exactly, oh, sorry, it's exactly as I talked about. um, um, so let's see the simple put operation. um, so now if you don't find the key in your LRU in your map and the size is less than the capacity, we can increase the size and then just insert our data in the map and also add the value to the end of our list. Uh, so what I explained was keeping the most recently used in the front. What I'm doing is keeping the most recently used at the end. Okay. Then if we already we find the key in our cache, then we just return. We can update the value with the new value that's been sent, and we can just call the get function to make it the most recently used item. Okay. Now what's get doing? Let's see. It finds the element, and if it does find the element, it looks for the element in our list, it removes it from our list, and it adds it to the end, which makes it the most recently used. And then it returns the value of the element that we found in our cache. So this is what would happen here also. Last case is when we are trying to add the element and our cache is full. So if we don't find the element and our cache is full, then since the first item that we have in our list is the in our LRU list is the least recently used, we remove it. We also find the item in our cache and remove it from our cache as well. And then we insert the new item in our cache and also insert the new key in our cache. Oh, sorry, our LRU list at the end, making it the most recently used item. We submit that. I've already done that before. I saw that it's not the best solution, I think, given here. I think that people have used other data structures as well, which work more efficiently for the test cases leetcode has given. But I think it's not going to be very far off from this. Yeah. All right. Hey, have you tried interview bit? Yes, yes, I have. Oh, that was old. YouTube links. Okay, I'll open that. GameCube Gorilla meme, but I upgraded. Nice. Uh, should not have opened that on stream. Anyway, it's done, I guess. Okay, let's move on to the next question. So I only did this yesterday. I didn't really get time for everything else. Um, okay, I guess we can do the other questions together then today. Okay. All right. So the question, oh, it's an easy question. Cool. The question is design a stack that supports push, pop, top, and retrieving the minimum element in constant time. Hmm. Oh, already done it. Not sure how this is easy. It wasn't very intuitive, but I think once you understand it, you're gonna get it easy. So essentially what we do is to get the minimum item in constant time, we always store the minimum in our stack. Yeah. Top, so the data structure we use internally is a stack itself. So to return the top, we return the top of the stack. Pushing, we see that if the element that we are adding is less than the minimum element, then we push the minimum element in again. So basically, before storing the minimum, basically before storing a new element, if it is the minimum element, we also store the last minimum element. So what that helps us do is that after we remove this element, we can remove the copy of the minimum element that we just stored and use that to update our minimum variable that we've kept. Because when we pop, say we popped the minimum element, Now we're going to have to update it, what the new minimum element is. Now we can't find it through the stack because that'll be on or any data structure for that matter. So what we do is we keep its copy just before our popped element. So we can pop again from our stack without actually changing it, because this was actually a sort of a hack value that we stored in the stack. As you see here, that the element that we pop, if it is the minimum is now the new minimum is now the extra value that we stored, and we remove that extra value as well, because that wasn't actually part of our data, but that's something we had stored for our convenience. Yeah. Oops, I think I hit the code again. Yeah. So get min is just return the minimum value. Top is returning the top of the stack. Push is if the new number is the minimum number, it is pushing the minimum number, which was the previous minimum number, and setting the minimum to the new number. And then finally, in either case, it is pushing the new number to our stack. For pop, if our stack is not empty, then we get the top element and we pop it. If the top element was the minimum element, then we um set the minimum element to the hack value that we had stored during push as stack top, and then we remove that value because that's not part of the actual data. Okay, moving on. Next question is number of islands. Medium, highly upvoted. Okay, given a 2D grid map of ones, which is lands, and zeros, count the number of islands. An island is surrounded by water on all it and is formed by connecting adjacent lands horizontally and vertically. You may assume all four edges of the grid are all surrounded by water. Okay. So I guess this would be 1. This would be 1, 2, 3. Okay. Hmm. Okay, let's start by writing something down. Since it's highly upvoted, I don't think it is an if-else question. It might be something else. Hmm. One, this could either be backtracking, where basically you start with the first index, the first one that you find, say. So basically an iteration on all ij's, and if grid ij is 1, then you call the helper function. What the helper function does is that it checks the borders, basically the right, left, top, and bottom of that index, and if If any of them is 1, if any of them is 1, it calls the helper function on all of those. Or on, not if any is 1, then on all of those. For whichever neighbors are 1, it calls the helper function on that. And before that, it updates the value in the original grid to set the current one as 0 so that that index is not checked on again. And after this recursive work is done, and we come out and come back to the for loop that we were making on our grid on every index, we will have set zeros on all the indices that are 1 and are part of an island. Is that right? I hope that makes sense. So for example, let's take the second grid. Let me draw that. Yeah, sorry. So I was saying when we come out, we add 1 to our answer. Basically, what this starting point did was cover a single island. So we add 1 to our final answer. Okay, so what I was saying was, say, yeah, so you start with this node, you set it to 0, which I accidentally did. So you start with this node, set it to 0, check its neighbors. Say you check the right neighbor first, you update this, set it to 0, you check its neighbors, you check this, update this to 0, check its neighbors, set this to 0. Then there's no other neighbor, so you come out, you come out of this, you come out of this, you come out of this, you come out of the first one. Since there's no other neighbors that are 1, you exit and you add +1 to your answer. Then you check for this index, then you check for this one, then this one, then this one, this one, this one. Since we're updating the original, these will be 0, these two. Then you take this one, then you come to this, you find a single one, you check all its neighbors, they're all 0, so you just update this to 0 and return and add +1. Then this one, this one, this one, this one, this one, so on. Then for the last one, you update it, check its neighbors, update it to 0, check this one, update it to 0, all neighbors 0, come out, add +1, check this 0, and you're done. So your answer becomes 3. So that's what it seems like. So it's medium, so it should not be very complicated either, I think. This does seem like a valid probable solution, although the complexity is not great, since backtracking is pretty bad. But what we're doing is we're doing n square uh, loop to check all the indices, and then in the helper functions we are going to be, for one node we could be checking n square nodes at worst, but that's going to be only for one node. So best case could be, I mean, not really best case. So if for n square we check, for one node we check n square, for other nodes we check none. So we can't say it's n square times n square. But say we check n square nodes and we call it, and the island is like 101010 and then 010101. So each helper function is called just once. So I think in the end it actually ends up to be n square only, which is not bad at all, since we obviously have to look at each element at least once to identify if it's part of the island or not. Okay, so int answer is 0, return answer, return answer for int I is 0, I is less than grid dot size I plus plus. Let's save these values. Uh, int uh, columns equal to grid dot size, int rows equal to grid 0 dot size. If grid dot size is 0, that's rows, sorry, rows, and that is columns. Grid size is 0, return 0 or return answer. Okay, this was rows for int j equals 0, j is less than columns, j plus plus, and we call the helper if grid I j equals 1, we call our helper function which passes the grid, to which is passed the grid, the index we are checking, the size of the grid just for sake that we don't have to calculate it again, rows, columns, and I guess that's it. And we do answer plus plus. Now what our helper function would be doing is we pass the grid to it, as int I, int j, int rows, and int columns. Now you set grid I j to 0. Then you check all the borders. If I is greater than equal to uh, if I is greater than 0, I is greater than equal to 0, and I is less than equal to less than rows. If sorry, if I minus 1 is greater than equal to 0, then you can go left. If grid I minus 1 j is equal to 1, now it's just ifs, so it's pretty pointless doing all this. Helper grid I minus 1 j rows columns. Let's copy paste this and see if we can get it done. If I plus 1 is less than rows, then grid I plus 1 is 1. Then you update this. If j minus 1 is greater than or equal to 0, then j minus 1 is 1. Then call it on j minus 1, I plus 1. If j plus 1 is less than columns, then call it with j plus 1. That's all. That should be it with no type. Sorry. Oops, I think I'm hiding my